All right, everyone. How are we doing today? Doing all right? How was everyone's break? Yeah, yeah. Too definitely being too short, and then uh, a a very long time ago, I actually took statics. I can't say it was my favorite class. It was it wasn't ever hard. It was just really tedious. Um, and then it gets a little bit weirder once you get into whatever the follow up is for that class, mechanics and materials or something. Well, okay, dynamics is different. Uh, um, sorry, I guess there's a point where I didn't continue on taking engineering classes, but there's one class where you have to deal with like deflections and materials, and I think that's different than dynamics. Maybe that's it. Well, the problem is there's a class called mechanics and materials, and there's another class called materials engineering, and I don't remember which one's which because I think the names are wrong. Yeah, the my experience with that class was very strange because the person who I took it from, it was their first year teaching, and they had never taught anything that wasn't a graduate level class. So they just taught the graduate level version of the class, um, which was a different animal. But anyway, weird weird asides aside. Our goal here is to begin chapter 14 in our textbook. Okay. It's the last step, even though it's a pretty long series of steps to preparing for our first exam in here. Okay. It turns out to be kind of a quirk of the schedule for our class here together that our first chapter exam is going to fall around the time we would take a midterm. Okay, in a normal class, I don't structure my classes typically around midterms unless it's a purely online class, and that's just the way it is. I do chapter tests instead, but it's going to function for us basically as a midterm. Okay, and then in the second half of the semester, we'll have shorter periods of time in between our two remaining chapter exams as we're leading up into finishing things up. But just to let you know, it's just the way the schedule works out. The answer was either give a short chapter test after 12 and 13, and then do another separate chapter test for 14, and then have two more after that. I decided not to do that. So that's where we are, course design wise. And would someone mind getting the door in the back? They're playing loud movies next door. I have to worry about A, you all and me being distracted, and B, the old DMCA demon. We don't want to have to fight them. Anyway, so for chapter 14, we are going to be working our way up to being able to fully deal with the calculus involved of multivariate functions. Okay. In chapter 13, we took a partial step in that direction. We dealt with the calculus of parameterized functions. So we had a vector valued function that depended upon one independent variable. Okay. Here, we're going to be changing things up and doing things a little bit differently. We're going to now have functions that map from Rm to Rn. Okay. So what that means is we're going to have m independent variables and n dependent variables. And it turns out that if we understand the calculus of this in this context, that once we kind of learn how to deal with things basically in 3D, except full 3D, we will understand in principle how to manage things if we move beyond 3 dimensions and can work with anything we like. Okay, the place we start is with functions of 2 variables, because those are the ones that still permit themselves to be visualized. So what we'll be talking about are functions that map R2 into R, or perhaps in a way that's a little bit easier to imagine the way that we think about these things, we're going to be making our variable z, the height, be equal to a function of the independent variables x and y. Okay? So this is how we're going to structure things. There are a few different ways to think about how all this works. Okay? And one of the visualizations that is shown in the text is useful because it gives us an idea of how we have to think about this if it's not a number of dimensions that we can graph all at the same time. Okay. Now, 3D, as we've talked about, is in some ways the upper limit of what we can conceptualize spatially. Okay. In terms of if we have 3 total dimensions, that's what we are able to graph in how we are representing our material. Okay. Now, mathematically, we will often be in situations where there's more dimensions than we can deal with. But this gives us a good idea of how we would think about these sorts of things. Okay? So what we have here is some 2-dimensional domain. All right? I've just drawn a blob. And what we can do is say pick an ordered pair that sits inside this blob. Okay? I have a function f. And what that function f does is it allows me to take a point from the blob and map it to somewhere on the number line. I can have some other point over here. It can get mapped to this point here, and so on, right? Okay. There's nothing that says these lines can't cross. Just because of the way that this all works. Okay. So the thing that's important about this and what makes this a function is the fact that for each of my points here in the 2-dimensional domain, that there's only one spot on the number line that they get mapped to. Okay? I don't have 2 arrows that point to different places that come from these points over here in the domain. There's only 1 arrow per point that maps it somewhere on the number line. Okay? So therefore, if we plot this in a way that has all of the heights set up, we would have something that passes the vertical line test. Okay? And what we would get is over this blob shape that would be the domain, and that's in the xy plane. Okay, we would have some surface up here that does whatever it is it does. Okay, so the independent variables in the xy plane define the domain. Okay, that's this part. All right, I'm not a good enough artist to try to do this one-to-one, okay, to try to draw the picture to where it's anything other than just a schematic. These arrows here tell me where the points in that domain map to and the height above it. Okay, sorry, these should all be vertical lines. All right, that's how you take this picture and relate it to this picture. So what we end up with is a surface that depends upon the two-dimensional coordinates of the input, which makes sense because that's what this says, right? I get the third element of the order triple from a function of the first two. And of course, this should remind you of this that we had from 2D. Okay, so question so far? Seems okay? All right. Now, the way that we handle this can be done in a number of different ways. All right, I've drawn kind of a visual idea of what some function may look like, okay? But in truth, there are many different ways to describe functions, okay? We can verbally describe a function, okay? This would be some kind of just English description or using some other language that tells us what the function is supposed to look like. Okay. For instance, one example of a function that is a function that's not mathematical would be the function that takes the name of a United States senator and maps it to the state that that senator represents. For each senator, there's only one answer, right? They are the elected representative of one state of the United States. Now, if you try to do that in reverse, where you give a state and then ask what are the US senators that represent that state, that's not a function because an input has more than one answer, right? Okay, so it's an example of a verbal function. Obviously, we can describe mathematical functions verbally as well, but something like that. Okay. The next example is one that shows up in your textbook. That is something that we don't do a lot of, but is useful, especially in a situation where you are working with functions and objects that you're not familiar with. And that is the table of values or numerical description of a function. Okay, so one of the things that happens in applications and is becoming more and more and more prevalent as we become more and more reliant on computers to do our work for marketing or social media or whatever it is we're doing, okay, is we collect tons and tons of data, right? You can collect data on how many people buy a product at a particular price point. For instance, gasoline, right? Fuel is one of those things that people buy, all right? And what you can do is figure out at particular price points, and we have all kinds of data on this, is how much fuel are people likely to buy at a particular price point or at a particular time of year. Both of those things would matter, right? So maybe you would want to describe a function that figures out what the demand is going to be as a function of price and calendar date. So that you, as someone who has to distribute refined fuel to all the different places, can know how to set up your load management for your systems, right? To make sure that we don't want the gas stations running out of gas right before Labor Day weekend, for instance. That would be bad. Okay? Now, the function for that mathematically is not something that we would describe by writing f of xy equals blah, right? What you would do instead is have a bunch of individual data points for different price levels at different stages during the calendar year, and then have a spreadsheet or something that collects all that information, and then you can interpret the ordered pairs or ordered triples that are described by that table as a function. Okay? And if you need to figure out the data points that lie in between two pieces of individual data you would do a process that's known as interpolation. To find the data points that lie in between, okay? Or if you need to find information that is outside of where your data grid lies, you perform a process that's known as extrapolation, okay? And so the difference between these, just to draw a little picture here, is that you're trying to find a dot that does not lie on the original grid, but is inside the bounds of the original grid, okay? For extrapolation, you want to know what's going on with this data point up here, so you have to go beyond. Okay. Numerical functions become more and more prevalent as you take other classes. For instance, I just did a lecture yesterday for my differential equations class in which we described a numerical approximation to a function, and basically what we did was we made up a table of values. And that table of values is the representation of a numerical solution to a differential equation. Okay? Because we picked a differential equation that we don't yet know how to solve, and the best we can do is use a scheme to approximate the answer to that as best as possible. Okay? The third way that we can think about functions is algebraically. Okay? This is where we would write down a formula. Okay? This is the one that we interact the most with in math class because it is the most efficient way for us to deal with mathematical functions, which is what we're doing here, right? Okay, but it is not the only way, all right? And one of the things that you need to become comfortable with is, as people who have mathematical knowledge and mathematical training, is be able to, when necessary, take the formula knowledge and communicate it in terms of one of these other ways of describing functions, if required, right? Because the idea is that we can often translate between these. I'm sorry. Should have used a different word here. Final ways visually, all right. One of the things that's nice to develop as we are working with algebraic functions, just to have in our mind's eye so that we have context for what's going on, is to be able to, at least to some degree, imagine what these functions look like. Okay? There should be patterns you recognize. If something is a circle or a cylinder or a sphere, you know what those equations look like, and you should be able to immediately picture what's going on in your brain. Okay? If graphs have parabolic elements or hyperbolic elements, those are things that we've talked about previously and should be identifiable, right? Now, obviously, I know that you don't have nearly as much practice in 3 dimensions as you do in 2 dimensions, but this is the point where we need to start thinking about these things to develop that understanding, because as we move forward in our class, we're going to have to do some geometric interpretations of these shapes and be able to, in particular, change the algebraic representation of a particular shape so that we can do calculus to it more easily. Okay, for instance, I can draw a right triangle, right? Okay, and I can tell you what this angle is and say that I have x values that go from 0 to 2 down here, right? Now, if I wanted to know what the height was at some point here, given a value of x, that's something that you could do, right? It's just a little bit of trigonometry. Okay? Now, the question becomes, if instead, whatever this height happens to be, right? I want you, for a given value of y, to be able to tell me what this height was. Could you also do that? The answer is obviously yes. Okay, I haven't given you enough specific information to be able to write down a formula that's not complicated, but this is the kind of thing I'm talking about. Okay, can you, using different variables, describe the same situation? Okay, because it may be the case that instead of integrating this way, we want to instead integrate this way, because it's going to be easier to do one of the ways as opposed to the other way. All right, and being able to change back and forth is how we're going to handle that. Okay, so this is what we're building up to. This is still a ways away, but this is one of the things to keep in mind. Okay, so I mentioned again in your textbook, they have a couple of really nice examples that they go through where they do numerical functions using tables and everything. They talk about wind speed and weather patterns. Take a look, okay? But we are going to focus on stuff that's a little bit more directly applicable to what we're likely to see for our purposes. And those are some algebraic functions and the visualizations of them, okay? Now, I, like your textbook does, am going to cheat and use computers to do a lot of these visualizations. So let's do a short exercise first, and then we'll use the computer to play around with some things. I don't know why that jumped so far, but here we are. Okay. So this is going to be a by hand sketch to get things started off for us. Okay. So what we want to do is we want to graph this thing here. Okay. And what we're going to be doing, of course, is like we would in 2D. For 3D, set z equal to f of x, y. Okay, so that becomes our third coordinate. And what this allows us to do is rearrange our equation here. And rewrite it like this. Okay, now, what is this the equation of? It's a plane, right? Okay, we can read off the normal vector of this thing. By reading off the coefficients there. Okay, now, if we want a quick sketch, all right, we can do the plane stuff, all right. But another thing to do that will give us 3 points, which is really what we want to be able to that will allow us to sketch the plane quickly, is we can set 2 of the values equal to 0. And figure out what the third one has to be, right? So if x and y are both equal to 0, then I'm left with z equals 6. If I choose z and x to be equal to 0, then that means that y is equal to 3. And I get 2 if y and z are 0. Okay? So what this does is it allows me to find the place where this plane intersects each of the coordinate axes, right? This is the z-intercept, this is the y-intercept, and this is the x-intercept. Okay? And then we can plot each of these points. We have 2, 0, 0 here. We have 0, 3, 0 here. And then up here we have 0, 0, 6. And this, is, of course, is just a part of the plane, but we can take for this the this triangle here. Okay, and obviously it's not just this part, it's the entire two-dimensional plane that this triangle lies in. Okay, but if you ever need to make a quick convincing sketch for a plane, doing a triangle or something is fine. Okay, because that triangle must lie in the plane. Okay. There is another type of object that is important to know. what its surface looks like as a two-dimensional function. Okay, and that would be something like this. And we have f of xy equals the square root of 4 minus x squared minus y squared. We again set this equal to z to make sure that we have a good picture of what it is we're looking at here. That allows us to square both sides. And doing some rearranging, we get this, perhaps. More conveniently written like this. Okay, this is the equation for what? Is it a sphere? Okay. Normally, we would think about this as the equation of a sphere, right? The problem is we didn't start with something that is a sphere. We have a hemisphere because the initial statement of the problem tells us that we're on the positive branch of the square root. Because if I write this, what does it have to be? What does f of xy imply? Has to be a function. And what do functions do? They pass the vertical line test, right? And so if I have the minus branch, I don't have something that passes the vertical line test. Spheres are not functions. Okay? Hemispheres are functions if I'm thinking about x and y as independent variables. Okay, so that's why it's only a hemisphere, because I need it to be a function. Okay, and so we can make our sketch. And put in our coordinates. Okay, so this is just an example of, again, another one of those things that we have to be a little bit careful about from the context of working with things that we're not used to working with. Okay, we're not used to working with three-dimensional objects, so we have to just be that extra bit more careful when we're thinking about what thing is a function, what thing's not a function, what is the context of our discussion. Okay, if we're just talking about equations, then it's perfectly fine for me to look at this thing and then do the whole sphere. Okay, but that's not what we're talking about. We're talking about functions. And so we have to use that extra bit of context to make sure that things are okay. More dimensions means that there are more things that might trip us up. Okay? That's why living in this world where we're talking about three-dimensional objects is something that we have to pay attention to, because we're on that cusp of running out of dimensions to be able to visually describe the things that we're talking about. Okay? And if we push past 3 dimensions in any way whatsoever, then we break the traditional sort of spatial relationship that we're used to describing functions in. But that doesn't stop a lot of these things from being functions. It just stops the way that we're trained to think about them from a relatively young age from being something that always works. Okay? So the idea of a vertical line test, for instance, is a useful idea as a way to double check yourself, but it is not a definition that you can apply as we push into higher level mathematics. Okay? So we have to be comfortable with letting go of some of these less robust tools as we press forward. Okay? But also, we, with more experience and more insight, gain some things that allow us to represent stuff in ways that's non-obvious. For instance, if we had something like, sorry, let me bring up a picture here. Hey, we're in Kansas. Okay, we've seen plenty of weather radar pictures. Okay, why does this picture have so many different colors in it? It represents intensity of the storm, right? Some kind of velocity or pressure differential that is in that environment, right? Isn't that a dimension that we're graphing for the purposes of showing this picture? Okay. So one of the tools that we can use is color to represent a missing coordinate axis. Because in some versions of this picture that you may have seen if you ever watched the evening news during a storm or when there's a busy storm system in the area, is they will show the three-dimensional version of this image, right? And they can show you the height of the storm in certain areas, okay? But they would still use color in the same way that they're using it in this to show the pressure differentials to determine where the areas of heavy rainfall are or where the storm velocity is the highest, okay? So we have ways to cheat, okay, to exceed that three-dimensional limit, but we have to press into things that aren't spatial, okay? The other thing that we can do, of course, is to show a time lapse of the picture, right? We can show multiple frames of what the storm has looked like every 10 minutes for the past hour or so to give you an idea of where parts of the storm are moving towards, right? And that's actually one of the most useful things. For instance, looking for stuff like this, okay? This is the most dangerous place to be, right? Does anyone know what that's called? It's called a hook echo, is what it's called, okay? The dangerous part of the storm is moving this way, okay? Because there's a high pressure region here and a low pressure region here. And the thing that you don't want to see happen is for the storm to turn around this low pressure region. Because if the storm turns around the low pressure region, what do you get? Tornadoes, okay? So when you're watching the radar, I'm not worried about what's going on over here. That's just wind and rain. Okay, what I'm worried about, and of course this is already after the hook echo has become the tornado, right? But what happens in the radar image prior to this is that the storm would happen here and you would see this tail kind of start to kick out, right? Or it would have kicked out maybe over here because the storm has started to, the storm is pretty clearly moving towards the west here. But you see that part in the storm and then it gets worse, right? Okay, this is a more pronounced version of what we would call that hook echo. Anywho, so here's another way that we can move into different kinds of stuff. Okay. So what I'm going to do now is write down a couple of formulas and show what the graphs of the associated surfaces look like. Okay, so let's start with this thing. We have the quantity x squared plus 3y squared times e to the minus x squared minus y squared. And what we want to do here is type in what this formula looks like. This is the website GeoGebra, as you can see on screen. It's a really nice way to do these types of visualizations because it will graph this stuff for us in real time. Okay, so we can zoom in. The website's going to run a little slow because I'm streaming at the same time as doing this. And then sometimes the figure also updates slowly. That function's a little bit complicated to do the graphs with. But what we see is these two peaks here that form as a result of what's going on with our function. Okay? And so what we would be looking for, of course, is figuring out, if we wanted to figure out what those peaks were, we would need some way to maximize this function, right? Taking derivative, set it equal to 0, figuring out where the tops of the peaks are for this. But it gives us the ability to graph different types of objects. Okay? So let's do another one. Again, I'm just borrowing stuff from the textbook here. Okay. This, we're going to take the sum of sine functions in the directions of both of our independent variables. And in order to generate these graphs, all we have to do, sorry, I need to change the letters here, is you just type some function letter as a name of x and y, and then you can type in the formula. And it's pretty smart about doing things like if you press shift and then 6 for the caret key, that's how you get exponents and things like that. You saw me type exp to get the exponential function. Okay, if you type log or ln, you'll get the logarithm, that kind of stuff. So we do sine of x plus sine of y generates our figure here. We can zoom out a little bit to see more of this. Okay. And if we turn it to the side, we see that we have sine waves in this direction. And we turn it this way, we see that we get the same thing, sine waves in the other direction. Okay. And it's a little bit smoother than maybe what we would get if we crumpled up a gum wrapper or something, okay, because it's smooth corners as opposed to a bunch of angular sharp things. Maybe it looks like the bottom of an egg carton. I don't know. Something like that. Okay, but again, just a different visualization. We can change things up. And instead of adding these two things together, we can multiply them together. Get a different kind of picture here. This really flattened out. Did I type things wrong? No, that's the example. What's the scaling on that thing? It's very strange. Okay. This one doesn't look quite as good as it did in the textbook. Anyway. Okay. If you need a visualization because you don't know what something looks like, all right, this is a tool that you can use for making this happen. Okay. For three-dimensional pictures, it is my recommendation that you use this. Otherwise, there's another website similar to this called Desmos that I prefer for two-dimensional graphs. But if you only want to learn to use one, GeoGebra is a little bit harder to use when you're getting started, but it has more features, including the 3D stuff. And for this class, the 3D stuff is probably overall more useful. So probably start here. But as far as just getting like a quick, I need to know what this surface looks like, that part's very easy to do. You just type in the formula. So practice, do 3 or 4 of these, get used to typing exponents and making sure your parentheses and fractions and everything look fine, and then you'll have that available to you. Okay. To finish up for overall the material in the section, the one thing that we didn't talk about today that we'll try to work in a little bit more next lecture is the idea of level curves and contours, which is another way for us to interpret what's going on with surfaces. But I wanted to try to talk about that in the context of something where we're using them to do something. All right. But it builds into the surface idea, and then we'll continue on from there. All right. Take care, everybody. Have a great one. Enjoy your week, and I will see you next time.